Welcome to lesson 32 of Additional Maths with Mr. Barrow. Today we're going to be looking at iteration. This is a GCSE topic, but I'm going to go into far more detail than you need at GCSE so that you understand it fully, why it works and what the point of it is. Okay. So before we look at this example here, I'm going to talk about the general aim of iteration. Okay. So you're used to solving equations of the form some function of x is equal to 0. So that function might be a quadratic, so you might have x squared plus 6x plus 5 equals 0. Okay, and you might solve that through factorization or the quadratic formula or completing the square. But sometimes you have a function of x which you simply do not know how to solve. And iteration is one of the numerical ways in which you can go about solving it. The first step is to rearrange this equation until it's in the following form. X is equal to some different function of x. Okay. So what you want to do is you want to make x the subject and also x being part of the object. And at this point, you then want to be able to find a value of x that if you substitute into the object as an input, that the output of f of x is the same value, is equal to the same value as the input you plugged in, that you substituted in. So once we get a point where this function creates a number, an output which is the same as the input it was put in, then we have solved the equation, because we want the value of x to be equal to the value of the function done to that value of x. So once we have got that, once the value of x doesn't change once it's put into the function, we have solved the problem. And iteration allows us to do that. So let's have a look at the question we have, and we'll see if we can turn it into this and see if this will work. So, show that x cubed minus x squared minus 1 equals 0 can be rearranged to make x is equal to the cube root of x squared plus 1. The first part of the question is usually given to you like this, so that you are given a way of rearranging to make x equal to a function of x. As we said, the aim was to get x is equal to some function of x. And here, this is what we have here. We have x as the subject and x in the object inside some sort of function. They do that. They tell you the result of that rearrangement because there are different ways in which we could have rearranged the original equation, and they will want you to do the way that they are prepared to mark. Okay, also the way that is the way that will work, because sometimes iteration does not work. So they will lead you down a path to get the right rearrangement that you want. So the first part is to show that question. All you need to do is show some algebraic steps that lead you from the equation you start with to a different rearrangement of that equation. Now, if I want x to be equal to the cube root of something, I probably came from a point where I had x cubed is equal to that something. So it looks like I'm going to need to keep the x cubed on one side of the equation and rearrange so that it is on its own on that side. So let's do that. So part one, if I start with x cubed minus x squared minus 1 equals 0, my next line is probably going to be adding x squared and adding 1 to both sides. So the x squared is equal to x squared plus 1. And then if x cubed is equal to x squared plus 1, then x will equal the cube root of x squared plus 1. And now we're done. We have shown that this can be rearranged to this. So I like putting QED. If it's a show that question, I like putting QED at the end. It's some fancy Latin, quod erat demonstrandum, which means basically, which was what we wanted, okay? This is what we wanted to show, okay? This is what we wanted to demonstrate, and we have done so. Okay, now the next part of the question has some scary looking algebra there. Well, it's not so scary if you have done some recursive algebra before, recurrence relations. And I'm going to explain what that means now, okay? So, some important understanding of what an iterative function is. So, what we have from the first part is we have a rearrangement of an equation. So, this blue bit is simply an equation. It will be true for a specific value of x, or maybe some specific values of x, okay? So this equation is not true always. This is true only for specific value. If I substituted in 25 into this, then I doubt I would get the fact that 25 would equal the cube root of 25 squared plus 1. Okay? 25 is not equal to the cube root of 626. So therefore, that equation only works for specific values of x. The green is a recurrence relation. We can use this with any values of x. A recurrence relation tells me that if I have a specific value of x, okay, so 7, I can find the next value of x using that previous value of x. So a recurrence relation takes a value of x, plugs it in to the function, and it outputs another value of x, and that is my next value of x. And then I could use that and plug it into the function to get my next value of x. So if I had the first value of x, so let's call it x1, if x1 were equal to 10, then I know that x2 would be based upon x1. x2, if I had x2, then n would be 1 to make x subscript 2. So then x2 would be based on the cube root of 10 squared plus 1, because 10 is x1. So if I'm finding x2, I use x1 and I square it, and then add 1, and then cube root it, and I get x2. And then I could keep going forever. I could keep substituting in the next value of x back into the recurrence relation to find the one after that. Now, the key thing is how to connect the two. Well, for the equation, I'm looking for a value of x which is the same in both sides of this equation. For this to be true, for this equation to be true, the values of x need to be equal. That will happen if, in my recurrence relation, if my previous value of x, when I substitute it in to the function, gives me the same output, so it doesn't change. If the recurrence relation converges to a specific value, then I have solved the equation. So if my previous value of x gives me my next value of x being the same thing, so it does not change, then I have solved the equation. So sometimes that will happen. Sometimes a recurrence relation will converge to a specific value. And if it converges to a specific value, it has solved the equation. If it diverges, goes away from values, then that won't solve the equation. That won't find a specific value for which the x on the left side of the equation is equal to the x value on the right side of the equation. Okay? The questions you will be given will generally converge. Otherwise, they will say, show using iteration why this does not solve the equation. And I'll show you using a graphical method what it looks like on the graph for it to converge and for it to diverge. Okay, so let's get back to our question. So use the iterative sequence xn plus 1 is the cube root of xn squared plus 1 with a starting value of x0 equals 2 to find a solution to the equation. Okay, so all we have done at this point is we have turned this rearrangement in the form x equals f of x into a recurrence relation, into an iterative formula. Okay, so we have said that the subject x on the left is our next value of x, and that is equal to the cube root of the object x is our previous value of x squared plus 1. And it tells you to start with a value of x0 equaling 2. So if x0 equals 2, then the first value of x will equal the cube root of 2 squared plus 1. So we substitute into the function the previous value of x to get the next value of x. The great way to do this on your calculator is to do the following. Simply type 2 into your calculator and press equals. You will then have 2 in the bottom right of the screen as the answer. The next thing you should type is the cube root. So on my calculator, that's above the square root button, so shift square root, so the cube root. And then put in answer. So don't type in 2, type in answer squared plus 1, all under the cube root. So answer squared plus 1. And press equals. Don't clear your calculator screen. So you then write down everything you have. I have 1.70997 ... I then don't want to bother typing that all in again and pressing squared and then pressing plus 1 and then cube rooting the whole thing. So all I need to do now is, because I have typed in the cube root of answer squared plus 1, it's still up there on the top left of my screen as the cube root of answer squared plus 1, but my answer is now 1.70997 ... So if I press equals again now, it will simply very quickly substitute this new answer in to that space on my calculator. So I don't have to type in anything else. I just have to press equals again, and it'll give me my second value of x, which is 1.577 ... Okay, and then you keep going. So the third value of x, press equals 1.5165 ... So that again, that has changed. So this is the third value of x is not the same as the second value of x. So I'm going to keep pressing equals a great many number of times. Okay. So you can, at this point, I'm going to take into account all the values of x that I'm doing. Okay, I'm going to write down the 15th value of x. So the third one was at 1.5165. So then press equals 1, 4th, 5th, 6th, 7th, 8th, 9th, 10th, 11th, 12th, 13th, 14th, 15th. And my 15th value of x is 1.4657 ... And if I press one more time, the 16th value is 1.46557 ... So it looks like this sequence is converging. It looks like this is converging towards a specific number and a number that rounds, because all I want is, I want the answer. It asks me for the answer to 3 significant figures. Okay. So I don't need this much accuracy. I just need a number which rounds to 3 significant figures. If I wanted to, I could use the sign change rule back to my original equation, where it equaled 0, and substitute values either side to check that my 3 significant figure answer worked. But it looks like my 3 significant figure answer will round to 1.47 to 3SF. So both of those are easily 1.47 to 3 significant figures. I could press equals many, many more times, and it doesn't look like it'll change very much in my calculator. The 9th decimal place is changing a little bit, and then eventually that will stop changing as well as you continue pressing equals. Okay, so 1.47 is my solution to the equation. So I would say x is equal to 1.47 to 3 significant figures. And I could check that if I wanted to using the sign change rule by substituting 1.465 and 1.475 into my original equation where the f of x was equal to 0 before I rearranged, and show that 1 was negative and 1 was positive, and therefore the root was within that region. Okay. So that is the iterative process. You first rearrange to make x equal to some function of x. You create a recursive formula, a recurrence relation, which then needs an initial value of x to plug in. You use this nifty way of using your calculator by putting in the initial value and pressing equals, and then putting the entire function we need with answer replacing xn. And then when you press equals, it'll get you, hopefully, converging to a solution. Okay. Now, it's time for you to have a go at one. I want you to show that x cubed plus 2 over x minus 5 equals 0 can be rearranged to what it asks for there. That x equals the cube root of 5 minus 2 over x. And then it wants you to use the iterative sequence given there, that x n plus 1 is equal to the cube root of 5 minus 2 over xn, with a starting value x0 equals 7 to find a solution to the initial equation to 4 significant figures. Okay, so pause and have a go at that, and then I'll show the answer. Okay, so the answer, part 1, is simple. It's only a couple of steps. You simply have to take away 2 over x and add 5 to both sides, and you get x cubed equals 5 minus 2 over x. And then that leads to the fact that x is equal to the cube root of 5 minus 2 over x. Then that turns into the iterative sequence we have here, this recurrence relation. And it tells you that x0 is 7. So I type in my calculator 7, press equals. And then I type in on my calculator the cube root of 5 minus 2 over answer. And when I press equals, again, it'll give me my first one. My first value of x should be 1.676764 ... My second value of x, if you press just, all you need to do at this point is press equals another time, 1.561479. And then if I keep going many more times, the 12th value of x is 1.5477688891. You probably don't need to go this far to get it to 4 significant figures. But I'm showing you that here that if you go far enough, it looks like almost exactly the same, even to the 1, 2, 3, 4, 5, 6, 7, 8, 9th decimal place. It hasn't changed from the 12th to the 13th value. So it looks like it's converging. And these both to 4 significant figures round to 1.548. You would probably have noticed that a little earlier than this. So x is equal to 1.548 to 4 significant figures. And you could check that by using the sign change rule if you wanted to, with 1.5475 and 1.5485 into the original equation equaling 0, and checking that one gave you a negative, one gave you a positive. So now, well done if you got that work, okay? What I want to show now is why this works. So just very briefly, I want to discuss what it looks like on a graph, okay? So here is a recurrence relation, okay? The n plus 1th value of x is equal to 2 minus the nth value of x squared over 4. And if I have that recurrence relation, which came from solving the equation where x is equal to 2 minus x squared over 4, I could solve it another way. I could solve it graphically by drawing the graph of y equals x and drawing the graph of y equals 2 minus x squared over 4, which are shown on the left, and seeing where they meet. Well, clearly they meet right at that intersection point there, which looks like at around 1.4 something. Okay? If I use an initial value of x being 1, this is what is actually going to happen on the graph. If I substitute x0 equals 1 into this recurrence relation, I'm always substituting the next value of x into this function here. So plugging 1 into that function will give me the y value up here. Okay, so that now is the new y value, which is about 1.7, something like that. So that's my y value on that graph. I want that to become my new x value. So if I then plug that y value into y equals x, so I'm plugging that y value into y equals x, it'll then go across to this value on the line y equals x. So that 1.7-ish value of y is now also my value of x. So now I'm at the point 1.7, 1.7. So that's my new x value. I'm going to substitute that new x value, 1.7, back into the recurrence relation. And I could go up from this point here, or I could just go down from that point there. And it'll give me that new output, that new y value, which is about 1.2 something, okay? And if I then plug that, if that y value then becomes my new x value, this is what will happen. 1.2 something is my new coordinate. And if I plug that 1.2 something into my recurrence relation again, I'll get this point here. And then what it'll do is it'll form a little cobweb where I'm going to get closer and closer to the solution. That is what iteration can often do. It will zero in on the solution by going round and round in a cobweb form until it gets closer and closer and converges towards that answer. Okay? But it doesn't always form that. This is called a cobweb diagram. It doesn't always form a cobweb diagram. It could form a step. It could step towards the solution. And here's another recurrence relation, where if I solve the equation x equal to root x plus 1, then it'll give me the solution to this. So I've drawn the graph of y equals x, and I've drawn the graph of y equals x root x plus 1. And the solution to both of them is where they meet. So if I substituted in x, the first value, if I chose x0 equaling 1, okay? So I would be substituting that into the recurrence relation. So I'd be substituting into this function to get a y value. So I would go up to this point. If that became my new x value, that y value becomes my x value. So I'd go to the y equals x line. where the y and the x values match. Then I plug that in. Then I go across, plug that in, go across, plug that in. So that's a stepping diagram towards the solution. So you're going to be stepping towards it, not going around the solution. Okay? So that's a staircase diagram. Now, here is one where it does not work. Okay? So if I wanted to solve the equation x equal to 10 over 2 to the power of x, I could draw the graph of y equals x and draw the graph of y equals 10 over 2 to the power of x, and the solution lies where they meet. And I could use the recurrence relation, x to the n plus 1th value of x is equal to 10 over 2 to the power of the nth value of x. Let's say I plugged in something close to the solution, plugged in 2. It would give me, in the recurrence relation, this value of y. Let's make that our next value of x. If I plug that into my recurrence relation, it'll give me this value of y. Let's make that our next value of x. Plug that in to my recurrence relation, I'll get this value of y. Okay, make that our new value of x. Plug it in, make it our new value of x. Plug it in, make it our new value of x. What's happening here is I am diverging away. I'm going away from the solution. I'm not going towards it. So this iterative formula is not going to work. If you kept pressing equals on your calculator, it would be changing by greater and greater amounts each time. So that would not give you a solution. So that's an example of when it does not work. Okay. You can look more closely at A level as to how to see when it will work and when it doesn't work. Here are the two examples we used. Okay, the one I did, I plugged in 2 as my original value of x. Here are the two graphs. If I plug in 2 into my function, it gives me that value of y. Make that our new value of x. Plug that in, gives me this new value of y. Make that our new value of x. Plug that in. So this is a staircase diagram going down towards the solution from above. Okay? And the one which was your turn, if you plugged in 7 into the function cube root of 5 minus 2 over answer, it gave you a number very close to the answer. It gave you straight away 1.67. As you can see, 7, if we go across that value of y, 1.67, is already very close to this solution. And if we plug that in, we get another number which is extremely close. Okay, so it didn't take very long in this one to step towards the answer. And this was another staircase diagram stepping to the answer from above. Okay, and so that's why it worked. So what you should do now is practice that iteration method. And there are some good questions where it talks about whether you're going to get a cobweb diagram, a staircase diagram, or whether your answer just won't work by giving you the diagrams to have a look at. Okay, and these are all in exercise 13.3. Okay, so the third exercise in chapter 13. So practice your iteration. It'll make you superb at it at GCSE, and it'll bring you up to an A-level standard in iteration, because that's one of the key numerical methods at A-level as well. Okay, so go away and enjoy, and I'll see you in the next lesson, lesson 33.